Monday recitation, into the middle. Wednesday, Friday recitation, out to the ends. Okay, so we're starting talking about volumes. We've talked about area and the difference between area and signed area, right? So the difference between area and signed area. Signed area. So what does the integral, just the integral accumulation function, find? Does it find signed area or area? You should be thinking signed area. Signed area, right, means anytime the function is above the x-axis, you get a positive contribution to that accumulation. Anytime the function is below, you get a negative contribution to that accumulation. So we get this like difference of areas or net area when you just do the straight integral. So if we want if we truly want area, right? If we've got it's above and below and we truly want the sum of the area, we got to finagle the integral, right? We either got to use absolute value or do something else to get actual area. Okay? So now we're going to talk about, we're going to move on to volumes of solids. And so here's the general game plan for that. What will it mean to use integration to calculate volumes? What will it mean? Here's what it'll mean. It'll mean first, we're going to form an empty shell from a curve. There's lots of different ways we can do that. Every problem will be different. But they'll give you some setup. They'll give you some curve and some explanation of how we're going to form an empty shell. Okay? And then we're going to fill the shell with right cylinders. And we're going to track the amount filled as we go. And that's the idea of a volume function, right? Accumulation of volume, accumulation of how much of the shell has been filled so far, right? And we talked about right cylinders. So we're going to use right cylinders to do that. And so if we're making a volume function, this requires that we know what? The key thing here is that we know the rate of change, right? Rate of change of the volume elements we're using. So what are the right cylinders that we're using? And what's the rate of change of that, the volume of that right cylinder according to how it's increasing, right? According to how it's increasing. Okay, so we said we were looking at the circular right cylinders last time. And what did we have last time? First of all, we looked at if you change, so we had this kind of circular right cylinder, right? We said if you change what's the rate of change of volume with respect to height? And we investigated this, right? So if the height is changing, right? If the height is changing, we went through the mathematics to figure out what would the rate of change be when the rate of change of volume of that right cylinder be when the height is changing. And what did we come up with? Yeah, we said after we did just going to review it on the video, after we did all the math, we said the area of that yellow base, right? The area of that yellow base ends up being the rate of change of volume with respect to height, right? So I guess we could write it this way. The rate of change of volume with respect to height was area of the base. And what was the area of that base? So the outer, so like the area of the whole circle minus the circle that's missing, right? So pi r outer squared minus pi r inner squared. Super important. So when that right cylinder is increasing in height, the rate of change of the volume with respect to height is the area of that yellow ring, or the area of the base. So now I want to do the same thing for, I want to investigate in the same way the other situation. So if you brought your sheet, you can get your sheet out. If you didn't bring your sheet, you can just recreate it here. Here's what we're working on. So now we're talking about the radius increasing, and I'm showing you that down here in the lower left-hand corner. The radius is increasing. Recall that the starting volume here was pi times 3 squared times height 7 minus pi times 2.5 squared times 7. And so in order to do this, we want to figure out what dV is if, so let's do 0.1. So what is dV? dV equals what if dr is 0.1. Now, what changes by 0.1? The inner radius, the outer radius, or both? What will change by 0.1? The inner radius, the outer radius, or both? Just the outer radius. The inner radius do you see that the inner radius is not changing in that animation? You see that? So all we care about, the inner radius stays, that outer radius is, we're thinking, if it increases by 0.1, what will the change in volume be? And so you're going to work through the math the same way we did last time, noting that the volume is, this is our volume of that thing statically. So what was our general form to get dV again? dV is going to be, in general, you said V sub F minus V sub I. Agree with that? That's right. So in general, it's going to be a final volume minus an initial volume. And each of those volumes is going to be calculated this way, right? The starting volume is going to be a difference. The initial volume will be a difference because there's a hole in it. And the final volume will be a difference because there's a hole in it. Okay? And then we need to figure out, and then what did we say? We said, if we can get that thing to look like something times, say, 0.1, then what is that something? That's the rate of change, because we know the rate of change is, given any change in radius, it's the thing we'd multiply by to give us the same change in volume. So we're going to write out the expression for the change in volume this way, and try to get that thing to look like this. If we can get that thing to look like this, then that's our rate. Because the meaning of the rate of change is, given any change in independent, the change in dependent will be that rate of change times the change of independent that you picked, right? dy equals mdx. Okay, so you got some work to do. You have a game plan? If you're not sure, get some help from TA or someone next to you. But you're either making progress or you're getting help. Trying to figure out what's the rate of change of cylinder volume with respect to radius. I gave you the game plan. Okay, go. Okay, did you make it this far? Check what I wrote and see if compared to what you did. Is it what you did or something close? So that first step is the change in volume. And then you notice that the inner ring stays the same. So when you subtract it, it's gone. Right? So you're just subtracting it here and actually adding it back here. So it goes away, right? It's the same exact term. Minus, and then minus a minus is plus. So what we're left with is those first two terms. Okay? Good. So if I lose you, ask, okay? And so then I notice there's a pi and a 7 in both. So I factor the pi 7 out, and I get 3.1 squared minus 3 squared. So here we're going to do a little trick. What we got is a squared minus b squared. What does a squared minus b squared equal? Difference of squares. What's the difference of squares formula? Do you remember? A plus B times A minus B. So I'm going to do A plus B. I'm going to go 3.1 plus 3. So there's a little trick here. And A minus B, 3.1 minus 3. Times pi times 7. And so I get what? 6.1. So what does 6.1 have to do with this here? What's the 0.1? That's dr. And so what would 6 be? 6 would be, yeah, our initial radius. So 2 times the radius plus dr. See that? That 6.1 is like 2 times the radius plus the dr. And what's 3.1 minus 3? That's dr. That's 0.1. Okay, so we're making some progress here. So what is the rate of change then? So what is the rate of change of radius with respect to height? So you see, I got my dr right there. So all this other stuff is my rate of change. Okay? Because the rate of change times the change in r gives me the change in v. Right? This is my change in r right here. So if we were to do this generically, right? If we were to do this generically, what did we really get? We got 2 times r plus, yeah, RO, plus dr times pi h times, I'll throw the dr at the end. Do you see that? And we know that in the end, in order to get exact volume, we're going to make what? The dr is going to be really small, right? So when the dr is really small, what do we get? What does this become? And the dr becomes really small. 2r outer plus dr. Just 2r outer, right? Times pi times h. Now, this one we need to keep. Even though it gets really super small, almost 0, we need to keep it as its value, because if we let it be 0, then everything goes away, right? So here, then we got dr. So as dr gets small, that whole thing becomes this. So our dV is that. So what's our rate of change? What is the rate of change of volume? Two pi r h. So if anyone got that before I did, that's excellent. That's tricky. There's some tricks to that to get that derivation. But if you got it, that's great. But now we want to look at that 2 pi RH. What is that about? So what do you notice about the 2 pi RH? What is 2 pi RH relative to this right cylinder? Okay, I heard circumference. It's kind of like circumference, but it's also got the h. I heard surface area. Surface area of what? The outside, right? The green part. Do you see 2 pi RH is the area of the green part? And which way is it growing? It's growing out, right? So it's growing out. So that face, that's the direction of it, the face, that's the direction in which it's growing outward, that amount of face is our rate of change. That's how much the volume grows for a change in R. It should make sense, right? The amount that the volume changes for a change in R is equal to the area of that green face. Because if you think about increasing it just a little bit, how much more volume you're going to get? It's going to be what? The amount of volume that you're going to get is going to be kind of like how much area there is there, right? How much area there is there. Is that similar to what we saw for the height one? Right? What was the rate of change of height? What was special about that? It's the area of the base. Same thing. The face for which it's growing, right? The face where it's growing is that base, and that's the rate of change of the height. The yellow part, and that's the direction that volume is growing. So you adding a little bit more volume is like adding a yellow ring, right? Adding a little bit more volume on this one is like adding a green sleeve, right? And that's why we get those rate of change the way we do. Okay, so what do we notice about this rate of change? It's the area of what? Of the lateral surface. And what's the meaning of the rate of change? What's the meaning of the rate of change? Anyone want to give it a try? What's the meaning of that rate of change? 2 pi RH. So if we haven't got it, today's the day. We're all going to get it. Volunteer. Yes, sir. Okay. But we've been working on a meaning for rates of change, right? A meaning. We're framing the meaning of rate of change. So that's a true statement. Yes, sir.
So I guess you could think of it as like adding just very, very small pieces to the existing volume.
Yeah, that's a good way of conceptually thinking about it. But we have this way of defining the meaning of the value of the rate of change. Yeah.
For each change in volume, there's a corresponding change in that cylindrical face that is 2 pi RH times the change.
Okay, he's got the right idea there. Yep, he's saying dV equals what? 2 pi RH times dr. So where do we start in this? Where do we start? We start with what? Given a change in radius. Given it here it is. If you haven't gotten it so far this semester, today's your day. Today's your day. Given a change in radius, the corresponding change in volume is 2 pi RH times that change in radius. So this is, hopefully that sounds familiar, because we've been saying it all semester. So given a change in your independent variable, the rate of change is that multiplier that will give you the change in the dependent variable. That's the meaning of the rate of change. Okay, and then we made sense of it, right? We said, okay, if it's the rate of change of volume with respect to height, then it's going to be like the area of that yellow ring, because it's like adding a little yellow ring to it, right? That's the rate of change. And if it's the rate of change with respect to radius, it's like adding a sleeve, right? Adding the green area is the rate of change, right? That's why it's the 2 pi RH. So these are going to be our two main rates of change as we're filling these shells. We're filling these shells, these empty shells, with right cylinders. We're going to determine what situation do we have. Do we have the height of the current shell changing, or do we have the radius of the current shell changing? And that's going to tell us. Then that's going to tell us what rate of change we'll have based on these two rates we came up with. So let's look at an example. Yeah, please.
So because it's constant, you would have to say for any small change, would you say for any change?
Oh, okay. So on the height one, we could say any change because it's a constant rate of change. But the rate, this one we just did is a changing rate because that sleeve is getting larger. So you're right. On the one we just did, you would have to say for a small change in R. Yeah, good point. All right. So for the one we did today, you have to specify that's for a small change in R. Because as soon as R changes, the rate changes because that sleeve is getting bigger, that outer green surface. Okay, good point. Other questions? Okay, example. All right, so what do we say? So here I've got the function sine x, and I'm showing it from 0 to pi. 0 to pi. And we want to revolve this part of the curve around the x-axis to form our empty shell. So can you imagine that? Can you imagine taking this curve and revolving around the x-axis all the way around 2 pi radians or 360 degrees. And can you imagine the shell that you'll get? How could you describe the shell, the empty shell we would get when we rotate that around revolve that around the x-axis? What's that? A pasta shell. Yeah, that's all the way closed, right? Usually those are like open, right? So it'd be all the way closed. Okay, let's take a look. Here we go. It's not rotating. Oh, because I got the wrong one. This one. Okay, so it's the same. Here we go. There it goes. Okay, so this is what it's like. We're rotating that thing around the x-axis. So the x-axis is now kind of coming out at you, and the y-axis is up. So that's what that thing looks like as it rotates around. And so then what will that shell look like? Think sports. Yeah, if you're thinking of football, that's a good way to describe it. I'm turning it as we go here. So there's our pasta shell, but then we go all the way and we get the football, right? Okay, so can you imagine? So you imagine that thing after we rotate it creates an empty shell. There's nothing inside, right? There's nothing inside, and so we're going to use right cylinders to fill this thing, and we're gonna take the x-axis and break it up into delta x intervals, just like we've done before on these previous examples. We're gonna break it up into delta x intervals, and for every delta x interval, we're gonna think about a right cylinder filling up that delta x cylinder, and so that looks like this. Here they come. So here my delta x is 0.2, and for every delta x interval of 0.2, for the current interval, it's gonna fill up with a right cylinder until I get the whole footballs filled up. Once again, watch it. So what do we have? Really, we have, at any given point, we have delta x intervals that are completed already. So we have the full cylinders filling up those delta x intervals, and then we have the current interval, and we have what? We have the cylinder growing in the current interval. So for this cylinder, what is changing in the current interval? Is the radius or the height or both changing in the current interval? The radius or the height of the cylinder or both? In the current interval. The radius or the height or both? In the current interval. We want the rate of change at the current value of x. So we're just looking in the current interval. So in that current interval, what's changing? The height or the radius or both? Just the height. If you said just the height, you're correct. The radius is staying constant. The radius is up and down, right? So the cylinder's turned on its side. The radius is the up and down dimension, and the height is the left and right dimension now. And so in the current interval, The radius stays constant, and that height grows until we get to the next interval. Now we have a new radius, but it stays constant, and the height grows through that interval. Okay? So I've got some questions for you about this. So work on these 4 questions, and I'll continue roll. Okay? Work on these 4 questions, and I'll continue the roll. And these are the ones I gave you. So number 1 doesn't apply to this problem in particular. It applies to any problem. Number 1, okay? And number 2. Number 1 and 2 is our general questions, not about this particular problem, but any. Okay? Go. Justin. Where's Justin? What'd you get for number 1? So you mean like sigma? So we want exact total accumulation. So what would that be? Okay. No, any volume function, right? So we don't have. So how can we represent? So what do you want to put here that means any? So it's going to be some rate function for volume, right? Of t dt. Is that total volume? Plus initial volume. If there's some accumulated volume already at 0, you need to include that as well. So this is the answer to number 1. Right? That's exactly what we talked about, the total accumulation function. Okay? What's needed to apply this general form to a particular shell being filled below? So if I want to now use this to find the volume function for this guy, what do I need? What's the key thing? The rate of change function, right? In order to write these accumulation functions, the main thing we need is the rate of change function. So I need that r sub v of t. And what'd you guys tell me? You told me what in the current interval, what is changing? Height is changing, right? I've got this growing cylinder, and it's growing by its height. So the height is actually, in the current interval, is dx, right? Delta x intervals are set, and in the current interval, the current height of that cylinder is dx, right? dx is increasing in the current interval from 0 up to delta x. All right, so what did we say when the height is changing? What did we say the rate of change was? So it was the area of the base. Area of the base. So in this case, what's the area of the base? Meaning area of the base. So it's even easier now because there's no hole in it. Pi r squared. So if you said pi r squared, that's correct. But what is our variable for accumulation here? Is it y or x? We're accumulating according to x or according to y? X, okay? So we need to know what that radius is in terms of x. So here's the rate of change is pi r squared. So what is r? R is this right here. What does that radius of that current disk equal? So here's a question we'll ask. Is it x? Is it y? Is it a change in x or a change in y? Is it meaning a big change in x, a big change in y? So is it an x? Is it the x coordinate? Is it the y coordinate? Is it a big change in x or a big change in y? Which one? It's the, you should be thinking it's the y coordinate, right? It's the distance from the x-axis up to the curve defined by here, so right here, right? So the radius in this case is just simply the y coordinate. Do you follow that? The radius of that shell that's growing is the y coordinate. But our yeah.
Okay, so I understand why it's y, but then y also equals sin x. So you can do it.
Yeah, that's where it's just going. Yep. So we need what is our independent variable for the accumulation? It's x. So we need that y in terms of x. So y equals, what does y equal in this case in terms of x? Sine x, because that's the function. So our rate function is pi times sine x squared. There's the rate function. Pi times sine x squared. Or the area of the base, because the height is increasing, right? The area of the base, because the height is increasing. So now we're ready to write this thing for our thing here. Ready? It is going to be, I'll fill it in here. It's going to be v of x. So here's how you put in GC. So v control 9 for a function, remember? Not shift 9 for parentheses, but control 9 for function, equals, and we want v of 0. What is v of 0? 0, because at 0, we haven't there's nothing in the shell filled up yet. So it's going to be 0. I can write that. We don't need to, but just so we're consistent with a total accumulation function. 0 plus integral is Control Shift I gives you the integral. And so it's going to be from 0 to what? No, volume function. We want the function of it being filled up. So 0 to x. And then we have our rate function. We got it. Are we going to put pi sine x squared? We need what? T. So now we're going to change these x's to t's because t represents all x values from 0 to x, right? And then we need squared. And then dt. Okay, and so now we just define that function in GC. And so if I wanted to represent and calculate the total volume of the football when it's all filled up, how would I represent? So thinking about the intervals being small, so make delta x really, really small, so it's indistinguishable from so the volume is indistinguishable from the true volume. And what will I write to represent the volume of the filled shell? What should I write to represent the volume of the filled shell? Someone got it over here. How about over here? How can I use what? But I want the full shell now. The filled shell all the way to the end. V of pi. You should be thinking V of pi. V of pi then represents, that's the function value for when x is pi or the whole thing is filled, right? That's because pi is our ending point. And so look, GC tells us what that value is. It tells us that that volume is 4.935 about. 4.9348. All right, now I want to represent half of that volume. How do I represent half of that volume? Is it V of pi over 2, or is it V of pi all over 2? It's the same. So someone said it's the same. So let's try it. V of pi over 2 and V of pi over 2. Is it the same? Yep, both of those are the same, and they're both half of V of pi. Okay, questions on setting up the function, using the function to get the whole volume? So this function now gives us, for any value of x, how much of the shell has been filled up that far, up till that value of x. So if we want the whole shell filled, we want to do x equals pi, v of pi, which is x is pi right there. Right? So when we do v of pi, we get the total accumulation, or the accumulation up to pi, which is the whole shell. Okay, any questions? New situation, here we go. Now we want to take that same curve and I want to rotate that around the y-axis. What do you get there? Think food. A bundt cake. Do they still have bundt cakes? That's what you get. Here we go, ready? So I'm going to revolve that curve again now around the y-axis, and I'm going to get this bundt cake, and I want to fill that shell. So filling that shell again using delta x intervals. If I use delta x intervals, filling that shell is going to look like this. Those are big delta x intervals, but it helps us to see what's going on, right? So in the current interval, what's changing? The height of the shell, the height of the cylinder, the radius, or both? In the current, okay, most of you are saying just the radius. See that height is constant and the radius is increasing. So we know we've got a shell whose radius is increasing, and we know what the rate of change of volume is with respect to radius. What is it? Did it earlier. 2 pi RH. That's our rate of change of volume when the radius is increasing, right? When the radius is increasing. Okay, so I got the same 4 questions, but answers 1 and 2 are the same. So now you're going to answer questions 3 and 4. So I want you to write out what the rate of change function will be, and is our independent variable x or y? Still x. This was all based on delta x intervals, so our independent variable is still x. So our rate function in the end, we want to get that in terms of x. So can you write the rate function in terms of x, and then write the volume function? Go. Okay, here we go. So the rate of change is 2 pi RH. But we got to get that in terms of x. So first of all, the radius of that current cylinder. Is it the x coordinate, y coordinate, a big change in x, or a big change in y? The radius. You should be thinking it's the x coordinate. That radius is the x coordinate. So we can write 2 pi x. The height of this shell. Is it the x coordinate, the y coordinate, a big change in x, or a big change in y? It's the y coordinate again. It's the y coordinate. So 2 pi x times y, and we need to get that all in terms of x. So it would be 2 pi x sine x. Here we go, quick. Ready? So the volume is Control-Shift-I, integral from, why isn't it working? Oh, I'm frozen. Blast. Okay. Or maybe that's what I need. No. All right. The rate. So it'll be integral 0 to x of 2 pi t sine t dt. If I want to get the whole volume of the whole bundt cake, how would I represent that? So this is v of x. The volume of the whole bundt cake would be represented as v of pi again. Question to think about. Is V of pi over 2, is that half of the volume? Is it half of the volume? Think about it. Think about it.